Hi, I just want to see if anyone is listening or if you can hear me. Let me know if you can hear me okay. Okay, cool. Thank you. Let's see. Start with, there's a few questions here already. Can you suggest any books for logistic regression? Actually, I don't. I know there's a few books about logistic regression. They're mostly from the statistics community. And I think they focus more on a traditional view of logistic regression that is not as needed today, or the emphasis is not as appropriate today. For example, many logistic regression textbooks that come from statistics literature, they focus on techniques for training logistic regression that are no longer used in large-scale situation. So I would basically, the answer is there's a few books, some of them more well-known than others, but I think they emphasize topics that are more traditional and classical and probably less relevant today for a data scientist. So I cannot really recommend one specific textbook like that for this course as a good introduction to logistic regression. You can try to, if you want more information, you can try to look at machine learning textbooks. Some of them may have a chapter on logistic regression. For example, a recent book by Kevin Murphy, or other machine learning books. Typically, they would have some material on logistic regression. If you do want to go the more traditional classical / statistics route, I think that's very interesting, and some of it is helpful, but I think a large part of it is not as appropriate for data scientists today. So I'm not aware of one book that describes logistic regression in, I think, a modern way, in a very thorough way, in a book that's completely about that. Okay, next question. Gradient descent uses an MLE log-based expression to define the cost function to be optimized through the derivative approach, right? Yeah, so let me try to maybe rephrase it in a little bit more general terms. Where the maximum likelihood estimator works with any likelihood. You form the likelihood or the log likelihood, and then you try to maximize that. The maximizer is your estimator. Whether you maximize it using gradient descent or using stochastic gradient descent, or using something else like Newton's method, or even something completely different, like maybe solve directly the equation of setting the gradient to 0. In some cases, you have a closed form solution for that, so you don't need any iterative algorithm. So whichever way you maximize the gradient, whichever way you maximize the log likelihood, whether by doing gradient ascent or any other method that could be very different from gradient ascent, based on gradient or not based on gradient, that leads you to the same answer, the maximum likelihood estimator. The solutions may be a little bit different if the log likelihood is not concave or strictly concave, because that would depend on the specific of the maximization or minimization procedure. Different minimization procedure, maximization procedures can be stuck at two different local maxima. And now, how does it connect to loss function? So machine learning is not necessarily dependent only on maximum likelihood. There are other techniques in machine learning to train a model, not just maximum likelihood. And in many cases, these techniques are based on the concept of minimizing the loss function. Now, in the case of maximum likelihood, you can define the minus log likelihood as the loss, and then the two approaches are equivalent. But there are cases where in machine learning, you can have a loss function minimization approach that does not correspond to maximum likelihood for some probabilistic function or model. For example, support vector machine. If you make a little change, you can get a probabilistic model. But if you just look at the original definition of support vector machine, there's a loss function that you minimize. It's called the hinge loss, and it's not that dissimilar from logistic regression actually. But the bottom line is there's no log likelihood with a probabilistic model hiding behind it that has the right interpretation. So I would say maximizing the log likelihood with gradient descent is maybe this big, and then maximizing the log likelihood with a different method, arbitrary method of maximization, is a little bit bigger, and then minimizing the log loss in general in machine learning, whether there's a probabilistic model or not, is bigger. It includes everything I've mentioned before and then some. But I think historically, or in practice, many machine learning techniques today are still using log likelihood-based loss functions, or loss functions that are based on log likelihood. So that's not in many cases, it's not a big kind of restriction, but there are cases where it is. For example, deep learning, and someone has some tricks and some models that do not clearly correspond to probabilistic models and maximum likelihood behind them. Okay, next. Once thetas are optimized, we should calculate the probability for all instances and then decide on the Y label, correct? Yes, that's correct. So you can do that for both the training examples in order to get the training error or the training accuracy, and the testing or held out accuracy or error, which is the prediction of the model on a held out data set. Either case, it's important that you know the Y's, so you hold out the Y's when the model computes its prediction, and then you reveal the correct Y label in order to compute the accuracy or the error rate, where the accuracy and the error rate are one minus the other. So if the accuracy is 90%, the error rate is 10%. And then later, if you want to actually use the model to predict in production somewhere, you want to set the model to work, put it to work, not evaluate it, but actually use it to help you do something or help your company do something. You don't need any more Y labels. You just get X vectors and you predict them as they come. Predict the Y label for every incoming X vector, and then you don't necessarily know the correct label in that case. And should we implement batch gradient descent or push for a stochastic solution? And so this is one of these cases where I want to push for consistency, relatively comparable in complexity. I don't think stochastic gradient descent is much more complex than regular gradient descent or the other way around, but I don't want every student to do something different, both because there are already a lot of questions. Should we do it this way? Should we do it that way? If every student will pick a small variation of the question, the number of questions and potential for confusion will grow a lot. And also, it will make it easier for the TAs to grade and to grade consistently. And so they, for that reason, I want to just keep regular gradient descent, just like I asked, rather than stochastic gradient descent. I think they're not that different, though. If you manage to program one, you can probably program another, and so there's some nuances, but I think both are very useful to know and to try. Okay, what's the next one? Next question. To determine the amount of iteration in gradient descent and figure out when to stop, should we just set a threshold like 0.01 for the difference between the current theta value and the new one? So I left the question of stopping or convergence criterion to you, so it's somewhat of an open question in that respect. What I think you should do, without me giving a specific prescription, is play with it a little bit. Don't just define, one threshold and say that's the right threshold, let me try it, and then report the results, and that's it. So try a few different options, like try, let's say, a threshold of, like you say, 0.01 and see how many iterations it takes, and then try to reduce it to 0.005 and see what happens to the number of iterations. And do a little bit of playing with different convergence criteria and see what happens to the result, to the theta vector, what happens to the prediction, and then them and report this in your homework. But mention a little bit of text on what you found out and why you chose the convergence criterion that you did choose. I do want to mention one thing that is important, and that is that the if there is no regularization, and there is no regularization in this homework, I do not ask you to use regularization. If there is no regularization and the data is perfectly separable, you can have theta parameters converging to infinity. So you could have something like theta 5 keeps increasing and increasing and increasing and increasing without stopping. And in that case, just bounding the change of the theta vector is not going to be sufficient, because it could be that theta will grow to 1,000, 100,000, a million, 5 million, 20 millions, keep growing to infinity, growing more and more and more, but the prediction of the model will actually converge. And so if you just try to bound the magnitude of the change in the theta vector, you may never converge in that case. And if you think of the loss function that you want to maximize, so this is concave. If it's concave like that, then there's a clear maximum that you're going to converge to. But what if it's concave like this? Right? Or let me do that again, like this. It keeps going up and up and up and up. It's a loss function. That means theta will want to get bigger and bigger and bigger and bigger all the way to infinity. And the log likelihood will keep increasing. So I didn't check for breast cancer Wisconsin data whether that can happen in this data set, but in general, that can happen. Keep in mind. Okay, let's see what next. How does setting the y binary values equal to 1 and -1 simplify the math compared to using 1 and 0? Yeah, so I think when you set it equal to 1 or -1, then you can write the probability of y given x using a relatively simple expression. And if you use the y equal 1 or y equals 0 convention, and you try to write it in a single formula, p of y given x equals, and you want that to be a function of x, of theta, and of y, I don't think you'll get a form that is as compact and as elegant as the y equals +1 -1. And that matters when you try to write down the log likelihood. You need to write it down based on the probabilistic model. So I think it's easier to write down the likelihood and keep moving from there. So I think it's a little bit simpler, the functional form that you get if you want to try to write P of y given x equals a single formula. Let's see. So let me know if you have more questions. I don't think. Oh, I did get. I'm going to pin for a second the office hour. Oh, that's the same question with the y's equal to -1 and 1 and 1 and 0. So if you have any more questions, let me know on the chat window. Maybe I can just reiterate in the meantime while you're thinking of more questions. I'll reiterate a few things that I mentioned earlier on the threads regarding the homework and classification, logistic regression in general. Regarding counting the operations, don't worry too much about which convention you're using and being super accurate, like is exponentiation equal to 3-time multiplication or whatever. Just count the number of simple operations like addition, subtraction, and count the number of complex operations like multiplication, division. And just report multiplication, division, and exponentiation. Just report the numbers and explain your reasoning. And don't worry too much. It's not going to be like an automatic evaluation where you give me a number, 350 operations or whatever, and I compare it to what I wrote down and it's different, so you get 0 points. And so it's not going to be like that. We're going to look at the methods that you use for counting and based on how reasonable that is. Remember, the goal is to measure effort by a computer, but to be super pedantic, you'll just never. It's going to become a huge question if I ask you to be super pedantic about that. But do think about it. I don't want to encourage people to just throw out numbers without careful consideration. The other thing with the formulation of logistic regression that I defined as compared to sometimes in the literature you see it with a minus index in the exponent. The two versions are comparable. You can train a logistic regression using both models, the log likelihoods that you get from either one. The only issue is that when you predict labels, you need to use the probability P of y given x of the model that you trained. And if you use the P of y given x for the model the way I defined it, and you want to have the prediction rule not be the y that maximizes P of y given x, because if that's the prediction rule, that's fine. You just need to be consistent with your definition of the probability model. But if you want to simplify further the prediction rule and just say y is positive if the inner product is positive or negative, then in this case you do have to flip it. So if the inner product is negative, you predict positive and vice versa, rather than if it's positive, you predict positive. I think this is something you have to keep in mind. So maybe there's something unintuitive in that. I concede the point. On the other hand, I do think the functional form is simpler. And when you do algebra, or when you do derivations of the gradient, or you write down the log likelihood, or you try to prove that it's the log likelihood is concave, or whatever you want to do with the likelihood or the model or the prediction and so on, it's just simpler to work with without the minus. So it depends where you want the complexity to be, I guess. What else was there? There was another interesting question in the threads about how to use the data. Is it categorical, factor, or is it numeric? And so in general, when you hear a question like this, the right answer would be go and research where the data is coming from and understand what the quantities represent. And if you don't understand the data, find an expert that does understand the data. But in this question, I don't want people to spend too much time researching breast cancer or medicine or the data set, where exactly it's coming from, or what does it mean, the shape, or mitosis, or whatever. So this is a homework. It's not a big project. It is a bigger homework, but I do want to limit the scope. So do one of the following: either treat all the variables as numeric. And by the way, you have to remember to remove the first column, which is the ID, and also remove the label, which is the last column, I believe, when you do prediction. So either you treat all the variables as numeric, or you treat all the variables as categorical, in which case you need to create fake dummy variables, basically. And just explain what you did. And I think if you choose the latter, it will be a little bit tricky given the size of the data. The data is not very big. So you will probably run into a situation like what I described, with thetas going to infinity. And that's not a huge problem. There are ways to handle that. For example, with regularization, or maybe you just say, I don't care if it goes to infinity. I'm just going to stop the gradient descent at some point. When it's converged to the right probability, I'm just going to stop and live with the fact that thetas are very big, but it doesn't bother me. So that's another way to deal with it. And so there are ways to deal with it. It's not the end of the world, but there's this probably bigger danger of this happening more, the thetas going to infinity, and also potentially overfitting if you treat all variables as categorical, because then the number of variables, the number of parameters become pretty big, and the size of the data is relatively small. Okay, let's see if there's another question. One follow-up on convergence. We conclude that we need to stop iterating based on theta values alone, right? Or is there other elements to keep in mind? So like I said, and keep an open mind and play with it. So try doing it based on theta and see what happens. In general, there's, like I said, a problem. And like I said, I don't know if that will materialize in the breast cancer data. I think it will if you use categorical variable representation. If you use them as numeric, it may or may not happen. I don't know. But there's potential problem of the thetas converging to infinity or to negative infinity. And if you just look at the norm of the theta vector compared to the previous iteration, that may not go down, may not converge to 0. In fact, it may grow and grow and grow as theta, one of the theta components want to grow, theta 5, for example, may want to grow to infinity. You can even add something like theta 5 going to infinity and theta 7 going to negative infinity. That's another possibility. So I want you to play with it a little bit. I want you to keep an open mind, think about it. And if things work out with just theta, then do that. Just think about it, try a few possibilities, write down what's your experience and so on. In general, in many cases, people just look at the thetas, but that's not likely to be a problem if you have regularization. If you do not have regularization, there may or may not be a problem with that. Okay, can you comment on how we can avoid local minima? So a lot of the iterative gradient-based optimization, like gradient descent or stochastic gradient descent, they are prone to getting stuck in a local minima or maxima, depending if you minimize or maximize. And that's actually a big problem, because that local minima may not be very good, or may not be as good as a different one. And you spend all this time getting good features and so on that you don't want to end up getting stuck in a bad local minima. But just to clarify, this shouldn't necessarily apply. This shouldn't apply to logistic regression that have a concave loss function, concave log likelihood or convex loss function. I do want to mention, maybe I should try to show you the whiteboard here. Let's see if that works. Okay, so I don't know if you see, but let me try to see what you can see. Okay, so I'm graphing here two curves, a blue curve and a red curve. They're one-dimensional function, but imagine them living in a multi-dimensional space of parameters theta. Both of these curves are concave. Okay, the difference is that the blue curve is concave and the red curve is strictly concave. Okay, so if you maximize your theta and your log likelihood is the blue line, your theta may never converge, may keep going to infinity. If it's the red curve, it will not go to infinity. So logistic regression could be the blue curve or the red curve. Could be either one. And if you use regularization, it's guaranteed to be the red. But we didn't study yet regularization, so I don't want to talk about it too much. So, but then you may have something like this, a green curve. Okay, so logistic regression may be the blue curve or the red curve. Don't worry too much about local maxima. Just have to worry about either getting to the maximum, or if the maximum is at infinity or at negative infinity, you just need to know at some point to stop. Because otherwise you'll never terminate the gradient ascent. But if you are working with other models, like deep learning, for example, you have a green log likelihood or a function you're trying to maximize that is like the green curve. In there, you could be stuck in the local maximum, a local maxima. So now getting back to your question, how do we avoid getting stuck in such a local maxima? The most frequent solution is to just start the optimization process multiple times from different starting points. So you start the gradient ascent one time from here, one time from here, one time from here, and one time from here. You just randomly generate a few points that you start the gradient ascent from, and when you start from here, you will converge to this maxima. When you start from here, you'll converge to this one. When you start from here, you converge to this one. When you start from here, you'll converge to this one. So what you do is you basically randomly initialize your thetas, and then you start gradient ascent. You see what you converge to, and then you start another gradient ascent procedure this time initialize from a different starting position, theta values. And you see where you converge there. And you keep doing that maybe 10 times. And then you evaluate the objective function that you try to maximize at each one of the convergence points, and pick the one that has the highest objective function, or log likelihood, or the lowest loss function. And so again, in the case of logistic regression, you can show that the log likelihood is concave. It's either like the red or like the blue, but it cannot be like the green. But other models may give you something like the green function, and then this is a significant problem. You have to think what to do in this case. Okay, let's see what's the next question. Okay, in the videos, you're referring to uphill and downhill without any visualization. Was lost a bit. Could you please explain or provide some pointers to reading videos? Yeah, so I think if you look at I don't have now a pointer ready right now for me, but if you Google a little bit gradient descent, you'll see this description of the process of going down a valley, or if it's gradient ascent, it's climbing up a hill. And the height of where you are in that process, let's pick climbing, okay? We should focus on climbing, a hill, gradient ascent. You have a function you want to maximize, like the log likelihood, or let's say like the red or blue curves that I showed earlier, and you're trying to maximize that function. And so imagine you are on the terrain, and the height that you're at is the value of the objective function, and your x and y coordinates are your current guess of theta 1 and theta 2. Let's imagine it's just two-dimensional theta vector. So you can walk around in the terrain and change your theta 1 and theta 2, which are your x and y coordinate. And as you walk around in the terrain, 1 and theta 2, you walk around, you also go up or down based on the terrain, if you're going up a mountain or whatever. And that height is the value of the objective function, or the log likelihood you're trying to maximize. So your task is to get to the x and y coordinates, or theta 1, theta 2, such that you are as high as you could be. So the y-axis is highest, or you are on the top of the hill. And the way to describe gradient ascent intuitively is, imagine you are on an uneven terrain, so it's a slope. There's a hill, and the gradient vector is pointing in the direction of the steepest ascent. Meaning, if you stand in a point and you compute the gradient, that's a vector in the x1, x2, or theta 1, theta 2 space. The gradient points in one direction, and if you follow, you walk in that direction, that is the direction that is the steepest incline as you change your xy coordinates. And if you think of it, even though it looks hard to do, you don't want to climb a very steep hill as a person. If you're an algorithm trying to maximize the log likelihood, that's exactly what you want to do. And you want to go the steepest, the fastest, the steepest, so that you can converge fast to the peak, rather than meander slowly and take some roundabout way, your algorithm longer to converge. But yeah, if you search Google a little bit, I'm sure you'll find more pictures of that. And if it's still not clear, send me a private message on Piazza, and I'll try to find more visualization of that. Okay, so I think think I'm out of public service announcement, and looks like addressed all the questions here on the comments thread. Thank you for listening. And I think there's a lag here. I'm not sure why, so I'm going to stop the broadcast, but I kind of keep seeing myself say as if I'm talking. Probably there's a 5-minute delay or something like that. So I hope I'm not going to chop off the last portion of the video when I stop the broadcast. If that happens, let me know, and I'll fill in the missing piece somehow with text or something like that. So bye-bye, thank you, and good luck with the homework.